In the next session, we're going to have a look at relative extrema of trigonometric functions, but it's worth here just looking at some of the basic concepts of relative extrema. We're going to start here by looking at the first derivative, and there are two things that we're going to look at here. So first of all, we need to get to grips with the concept of stationary points. So at a stationary point, we are talking about somewhere at which the gradient is 0. So if we look at this function here, we can see that at this point at the origin here, if I was to draw a tangent line, the gradient would be 0. So if the gradient of a point is 0, we have a stationary point. So we should be able to see that we could find the x-coordinates of a stationary point by finding the first derivative and setting it equal to 0 and then solving for x. That would enable us to find the stationary point. We can actually establish the type of stationary point, whether it's a maximum point, a relative maximum, relative minimum, or indeed something else, by looking at what's happening either side. So we need to understand the concepts of increasing or decreasing, where the slope is negative. So where our derivative has a negative value, we would say that in this interval here between -5 and 0 it is decreasing, and here in this interval between 0 and 5 it is increasing. Where the gradient changes from decreasing to increasing like it does here, we would have a minimum point, and similarly where it changes from a positive or increasing to a decreasing, we would have a maximum point. So this is in essence called the first derivative test. So if the derivative changes from positive or increasing to negative or decreasing, then we have a relative maximum at this point. Similarly, if it changed from a negative to a positive, then we would have a relative minimum at that point. And we can see this on this graph here. So we've got in this region the gradient is positive or increasing, and then at this point here it changes to negative or decreasing, so that means that's a relative maximum. Here we can see there's a relative minimum because it is decreasing, or the derivative is negative here, and at this point it changes and becomes positive. You'll note here that even though the gradient at this point is 0, on the left hand side we can see it is positive or increasing, and it is also increasing or positive on the right hand side. So this is neither a relative maximum or a minimum. Just to remind you the concept of global extrema, if I was asked to find the global maxima or minima of this graph, I can see that the global maximum would be this point. This is the largest point everywhere in this region, and similarly this is the global minimum. So relative maximum, the clearly identifiable maximum in this area, and similarly clearly identifiable area here for the relative minimum. The two concepts that we need to be familiar with. A critical number then is where the derivative equals either 0 or might be undefined. And if it is 0, we say it's a stationary point. So a stationary point here is a special case of a critical number. So here are three questions to have a go at quickly. Use the first derivative test to find the relative extrema for the functions. So determine the nature of the stationary points and find their coordinates. For the first part then, find the derivative, so that's the first derivative. We can factorize that and set that equal to 0 in order to find that there would be a stationary point at x equals -1 and x equals 2. And then all we're going to do is substitute in a value in each of these intervals here. So for instance here, I might take the value of 0, substitute it into my derivative, and I end up with -12. So these values will be negative. Substitute in points here, either side, you can see these will be positive. So if we have the first derivative which is changing from increasing to decreasing, we can see that this must be a maximum point, and here if the gradient is changing from a decreasing to an increasing, this must be a minimum point. So we can therefore find the coordinates by taking the x-coordinate of the stationary point and substituting it back into our original function to get the y-coordinate. So f of -1 is 7, f of 2 is -20, so we have a relative maximum at -1, 7, and a relative minimum at 2, -20. The second one, part B, we're going to use the quotient rule to differentiate, and we can elicit here that if we set this equal to 0, either this equals 0, in which case x equals 0, or this equals 0, in which case x equals plus or minus 1. So in order to look at the stationary points, we found the x-coordinates of the stationary points, test the derivative in these intervals here, and we can see that there is a relative minimum at this point at 0 because the gradient changes from negative to positive, but here and here the gradient doesn't change. It's negative either side, so these are neither maximums or minimums, so we can only conclude that there is a minimum at this point, and then again we can find the y-coordinates by taking this value of x and substituting it back into here and yielding an answer of 0, 4. But see then, differentiate gives us 3x squared, set that equal to 0, which means x equals 0, so there's a stationary point here. Test the derivative either side, and it's positive, so there is not a change, and therefore this is neither a relative maxima or minima. Just to remind ourselves then of the second order derivatives, or indeed higher order derivatives in general, have a quick go at these two questions. So in the first instance, we're just going to find the first derivative and then find the second derivative, and we can just then tidy this up by expressing it as 6 over x cubed here. That should be fairly straightforward. The second part, a little bit harder, some trig calculus here. We're going to have to use the chain rule to differentiate this in the first instance to give us negative 2 sine 2x. Take the derivative of this to give us negative 4 cos 2x, and the derivative of this to give us the third order derivative, which is 8 sine 2x. We're asked to find the third order derivative of pi by 8, so if we substitute this back in, we are therefore effectively finding 8 sine pi by 4. Pi by 4 is the same as 45 degrees. Sine 45 is 1 over root 2. And we can rationalize the denominator here, so this would be the same if we multiplied top and bottom by root 2, which would give us root 2 over 2. And if we multiply that by 8, that's just going to give us 4 root 2. Okay, so looking at the second order derivative then here, we are concerned essentially with concavity in the first instance. So suppose we have a graph here, we can see that the rate of change of the gradient is decreasing. If we look here, we've got a steep positive gradient, a less steep positive, 0, a shallow negative, a steeper negative, and a steeper negative. So the gradient is getting lower and lower. So in this instance here, we would say that it is concave down, and the second derivative is less than 0. At this point here, we will see that suddenly the gradient will start to get larger. So it'll be less negative until 0, and then a small positive, and gradually larger and larger, more positive. So the rate of change of the gradient is increasing, and therefore it is concave up in this region here, because the second derivative would be greater than 0. So let's have a look at trying to find the second, or use the second derivative to find the intervals where the function is concave up and concave down, and then use this to find the inflection points. So in the first instance, the first derivative is going to give us 6x squared minus 6x minus 12. The second order derivative, if we differentiate that, will give us 12x minus 6. Set that equal to 0 and solve for x will give us x equals a half. So we need to try and test the concavity either side of this. So we can substitute a value either side, for instance 0 to the left into here, and that will give us a negative value. If we choose a similar point on the right, we'll get a positive value. We have an inflection point when there is a change in the concavity either side. So the second derivative at this point is 0. We know that because we've set it equal to 0. And there is a change in concavity. So where you have the change in concavity, we will have a point of inflection. So this is the point of inflection. Here there's a change in concavity, and the second derivative is equal to 0. So that's what we've got here. So therefore it's concave down between, well, negative infinity and a half, and concave up, where the second derivative is positive, between a half and an infinity. So therefore there is a point of inflection here, and to find the y coordinate we're going to take our half and substitute it into our original equation, which will yield us an inflection point at half negative 13 over 2. The other reason we need to use the second order derivatives is as an alternative way of identifying relative extrema, i.e. a relative maxima or minima. If we have a second order derivative greater than 0, then we must have a relative minimum, and if the second order derivative is less than 0, there must be a relative maximum. So we can see at this point here, the gradient is negative, but it's getting less and less negative, and becomes positive and more positive. So the rate of change of the gradient here is positive, i.e. we therefore have a minimum. Conversely, at this point, the rate of change of the gradient is decreasing, so it's less than 0, and therefore we must have a maximum. So we can use these to identify the relative maximum, unless, of course, we get a second derivative equal to 0, in which case we have to go back and use the first derivative testing either side. So just to finish, have a quick look at these. First of all, then find the first derivative and differentiate that to give us the second derivative, which is 6x minus 6. Set that equal to 0, and then factorize so we can solve to find that there are two stationary points at 0 and 2. Find the second order derivative of 0, and that tells us it's negative, so we have a relative maximum at this point. We can then substitute in, so if we've got the x-coordinate, we've identified it's a maximum, we can then substitute in f of 0 into our original equation to find the coordinates of the relative maximum. Similarly, we can test the second derivative of 2 and establish that is greater than 0, therefore it is a relative minimum, and then we can substitute back into our original function here to find f of 2, and that will yield that, this should say 2, it should be a relative minimum at 2, negative 6. Finally, part B, first derivative and second derivative, we can factorize and set it equal to 0, so we would have a potential stationary point at 0 or plus or minus 1. If we find the second derivative of 0, the second derivative test fails, it doesn't work, so we don't know whether it's a maximum winner for that. If we take a negative 1, that gives us a negative value, which means it's a relative maximum. We can find the y-coordinate there by substituting negative 1 back into our original equation, so negative 1, 2 is a relative maximum. Similarly, by testing for f of 1, we get a positive value, which means it's a relative minimum at the point 1, f of 1, which is going to give us negative 2. So we can establish then that we've got a graph here, and if we're looking at the first derivative for our initial point, we can see that it's negative both sides. So just by substituting a value either side, this would tell us it's neither a minimum or maximum.